Well, good morning. This is 11:34. Sorry. On Tuesday, the 17th of September, and we do have a student here. I was just starting to say I'm in here by myself. But here we have Keyston here. I left my reading glasses at home, so it's going to be a weird day for seeing well. Okay. While we're waiting for the projection to come up, let me go over a few announcements. I've fallen sort of behind on these. Today's the 17th of September. And coming up tomorrow, our volleyball team has a home match against Southern Union, and that will be at 5 o'clock in the afternoon. So if you happen to be near the Birmingham West Campus at 5, stop on in to the gym and watch the volleyball team hopefully whoop up on Southern Union. And that's tomorrow, Wednesday. Thursday, they'll be playing at Bevel State up in Fayette, Alabama. So if you happen to be heading that way, that match is at 6 o'clock. And then, I'll wait and do the rest of those later. The Scholars Bowl team is currently recruiting players with knowledge of any subject, including history, literature, science, music, current events, mythology, mathematics, you name it, they'll want you. Okay, so you can check with the coach, who is Mr. Matthew West, and his office is right down the half flight of stairs there, just past between 259 and 261. That's his office on the left-hand side. You'll be glad to talk with him. Now, the presentation was last evening. That was the Miss Esther Levy, daughter of Toby Mornick Gerson, spoke about her mother's personal experiences as a Holocaust survivor. But the presentation, the exhibit, is still over at the library on the Birmingham West Campus. That will be there through next Monday, I believe, is September the 23rd. Okay, so take advantage of seeing that there. And the NASA's Community College Aerospace Scholars Program is, they are receiving applications for that. The deadline is October 16th. There's a great poster down the hall, about halfway down the hall here on the left, about NCAS, and shows several of the Lawson students who have participated in the past. And they all look like happy campers because it's a good program. All right. We'll see if anyone else shows up. Peyton or Charles. Don't think Jasmine's going to be joining us, so we haven't seen her yet, so I doubt if she's going to show up. But we saw Peyton for the first time last time, so maybe we still have hope. All right. Now, my memory is that we finished chapter 1 last time, and don't think we got started any on chapter 2, did we? Okay. Now, we've already been dealing with matrices, and that's the title of chapter 2. But we've just been dealing with them and how to use them to solve systems of equations. Now we're going to be talking about the various operations that you're allowed to do with matrices. Sort of like, I don't know if you remember way back when you dealt with real numbers. Well, let's start with integers the first time. You added, subtract, the operations you can do with them. Then you moved up to real numbers and you were able to do other things with them, like take square roots and things like that. So what are some of the operations that we can do with matrices? Well, one of the first is almost one of these things. Do you really have to go over this? But I guess they thought we did. In section 1.2, you use matrices to solve systems of linear equations. And this chapter introduces you to some fundamentals of matrix theory. And by the way, I did give you the test last time, right? Okay, good. Fundamentals of matrix theory and further applications of matrices. Standard mathematical convention to represent matrices in one of the following three ways. Okay? One, let me get my pen set up. Again, not having my reading glasses. Everything at a reasonable distance is blurry. I have to get way back for it to come into focus. You can refer to a matrix as an uppercase letter. A, B, C, something like that. Okay? Another way is to show a representative element. I can't spell. I can't see what I'm writing either. Element. And that would be in brackets such as A, I, J. Make sure they are using the same subscripts I am. As well as I can see they are. B, I, J, C, I, J. Now, it's not always the case, but it's very common. If you name the matrix capital A, then you refer to its various elements as with little a with subscripts. Okay? Of course, what does those subscripts represent? The I is the row number and the J is the column number. Okay? So that these two representations would be of the same three matrices. And you could do others like that as well. And then the final way is actually write out the matrix, okay, as the rectangular array of numbers and we say numbers. You can have letters, variables, or other things in there as well, but usually they're numbers. But since we're not going to assign them numbers, we're going to represent them just like we did before. A11, A12, A13, dot, 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 A1. Do they use M or N? It looks like an N from where I'm sitting, so I think that's an N. Okay. A21, A22, A23, dot, 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 to A2N, A31, A32, A33, dot, 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 to A3N, and then dot, dot, dot on down till you get A sub M1, A sub M2, A sub M3, dot, 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 to A sub Mn, with dot, dot, dots everywhere in between. Okay. So that's how we would represent it as a rectangular array of numbers. Of course, if you had a rectangular array, you list them all, but this is trying to leave it open to as small or as big as you need using M rows and N columns. The I stands for the row number and J little j for the column number. Okay. Now all that was, well, maybe not all that was pretty much covered. Certainly the conventional rectangular array of numbers we did in the first chapter. I don't know if we mentioned the upper class or other way to represent it. Now, the matrices in this text are primarily real numbers. There's no real reason you can't use complex numbers in them, but this text is going to stick with real numbers, which is good. Okay. That is, the entries contain real numbers. Okay. And so we'll be dealing with real matrices because all the entries are real numbers. All right. Now, the next little definition here, and I'll go to a clean page, is a definition of equal matrices. When is a matrix, one matrix equal to another? When all the entries, every entry, all the corresponding entries are equal. Two matrices are equal when every corresponding entry is equal. Okay. Now, another way to express this, they give in the definition just below the middle of the page there, two matrices, A equal, and this is going to use two other ways to represent it, little a ij, and B, which of course is represented by little b ij. Now, they are equal. Here's two things that have to be met. They have to have the same size. You can't compare a 2 by 3 matrix with a 3 by 2 matrix. Well, you can, but they can't ever be equal because they're not the same size. Even though they both have 6 entries, that doesn't matter. They have to be precisely the same size. Okay? And we'll call that size m by n, where m represents the number of rows in each of those, and n the number of columns of each of those. And a sub ij is always equal to b sub ij, okay, for, and this is sort of how you represent this, 1 is less than or equal to I is less than or equal to n, because that's how many columns you have. No, I'm sorry, that's rows. I can't read. Okay? And j, and 1 is less than or equal to j is less than or equal to n, the number of rows that you, columns that you have. I'm saying everything backwards now. So every one of those entries, as long as the i's and j's are identical, for all the i's between 1 and m and all the j's between 1 and n, every A32 is equal to B32. Yeah. Has to be equal, every one of them. Now, as I said before, sometimes you might put a variable in there, but if that's the case, if A17 is 12 and B17 is x, x has to equal 12, okay, or x plus 3, then x would have to equal 9, you know, so you would have to have so the entries are identically equal. All right. Simple enough concept. Let's do example 1. Okay? Here's matrix A. 1, 2, 3, 4. Really creative. Okay? Here's matrix B. 1, 3. Matrix C. I believe that says 1, 3 also. And matrix D. 1, 2, X4. This is what I was mentioning before. Okay? Now, can A be equal to any of those others? It could be equal to D. Why couldn't it be equal to B? Wrong size. Same thing with C. Wrong size. Same size as D, what would be the requirement for those to be equal? X has to be equal to 3. Okay, how about B and C? Could they be equal to each other? Again, wrong size. Even though they both have 2 entries and the 2 entries are the same, still not equal because B is a what? 2 by 1 and C is a 1 by 2, and those are not the same size. So absolutely correct. Okay. Now, B is sometimes called a column matrix or a column vector. Okay, it could be called could be just called a matrix. That's fine, but because it only has 1 column, it could be considered a column matrix, which it is, or because it only has 1 column, a column vector. Okay, vector being a one-dimensional structure, a matrix can be bigger, but a vector can only have 1 dimension to it. Matrices could have 2 dimensions, but a vector, one of those dimensions is going to be 1. So that would make C what? A row matrix or vector. A row matrix or a row vector. Okay. So anytime you have a one-dimensional matrix, in other words, it either has a single column or a single row, those are matrices, but they can also be identified as vectors. Okay. Now, bold-faced lowercase letters often designate column matrices and row matrices. However, if I saw them, I would call them vectors, because that's the standard representation for a vector is a lowercase bold. Okay? Now, let's do vector A here, matrix A here, and say, well, what if we took just the first column here and called that A1, and this is bold. I can't write bold, so I put an arrow over it. That's why I think of them as vectors, because I think of things with arrows over it as vectors. Would be 1, 3, and A sub 2 would be 2, 4. Okay? Now, you could then write matrix A, capital A matrix, as the joining of vector A1, and they put this vertical line there with A2. vector A2. Put that inside brackets, and that indicates you've conjoined, you might say, two column vectors or two column matrices. Okay. Now you could do the same type thing for, they don't do it, but I was trying to think what would be the best representation. Since we've already used A1 and A2, let's just go on and use A3. You could say was a row vector 1, 2, and A4 was a row vector 3, 4. Then you could say matrix A, same matrix we have here, is A3, I forgot what I named it, row vector A3, then put a line, just like you did a vertical line here, a horizontal line there, A4. Now, they didn't go into that, but you could do it. That's also a legitimate representation. So they bring that up, and this is called augmenting the matrices. Remember, we augmented the constant terms with the variable matrix, and this is, so it's the same type deal, only before this was a matrix, not a vector. That was a vector, okay? And we augmented it that way. And that's, I think, where I got into the habit of drawing a vertical line to help remind myself. I usually did a dotted vertical line just to remind myself that was the adjoining part. This one doesn't do that, so I tried to get away from it. Okay. So, equality of two matrices, that's one matrix operation you need to understand. And pretty straightforward and hopefully pretty simple. Well, how about addition, subtraction, and then also scalar multiplication of two matrices? And we did this before. I'm pretty sure we did, but we'll do it now again. To add two matrices, and a guess, you have to be the same size. It doesn't make any sense to try to add a 3 by 2 to a 7 by 4. It's not going to work, you know, because you don't have corresponding entries for every one of those. So to add two matrices of the same size, add the corresponding entries, okay? And here's how you express that as a definition. If capital A is represented by this matrix A sub ij, and capital B represented by this one, B sub ij. Now, the reason we use the same letters is to emphasize to you they have to take on same values as each other for this to make sense, okay? Now, I is any number between 1 and m, j is any number between 1 and n, okay? They have to be the same size, and we'll call that, just because I just said it, m by n, m rows, n columns. Then the sum is when you add the two matrices together, is also an m by n matrix, and this time that sum will be A sub I j plus B sub I j. Okay. Goodness gracious. This is getting so hard to read. It makes me feel almost dizzy. Okay. It's also an m by n matrix, and they actually, that is a plus sign there. My writing's not too good either. This is A plus B. This is how you add two matrices. You add for every entry, I and j, you add the aij to the bij. All right. The sum of two matrices of different sizes, not defined. You cannot do it. So let's go to example 2. Pretty easy stuff here. And let's add some matrices. Gracious, my eyes hurt. Got one more long class today. This is negative 1, 2, 0, 1, simple 2 by 2 matrix. So add to that 1, 3, negative 1, 2. Do you think we can add these two? Yeah, they're both 2 by 2 matrices, so you can add. What was your first entry? 0, second entry. 5, third entry. Negative 1, fourth entry. 3. Okay, there it is. You have added the two matrices together, 0, 5, negative 1, 3. All right. Here's the B part of example 2. This is 0, 1, negative 2. Goodness gracious, that came out ugly. I was just writing and not paying close attention. 0, 1, I wasn't holding tightly on this and it moved and got well out of shape. 1, 2, 3 plus all right, what does that yield? Adding those two matrices together. Okay, 0, 1, negative 2. You know what the, goodness, I can't write. All right. What's a little bizarre about that? Number one, it's okay to do because this is a 2 by 3, that's a 2 by 3, so you can't add them. But what do you notice? You got the same thing you had here. And this is a way of expressing a rule we're going to come up with later, that A plus the 0 vector is always A. Just like 7 plus 0 is always 7, okay? The 0 matrix acts just like the number 0 does when you're adding. It doesn't change the value of the matrix being added at all, okay? C here. One, negative 3, negative 2. Now, help me if I'm misreading some of these numbers. Plus negative 1, 3, 2 is equal to what? Yeah. All the way down. Negative 1 plus 1 is 0. Negative 3, or 1 plus negative 1 is 0. Negative 3 plus 3 is 0. Negative 2 plus 2 is 0. And these are called the additive inverses of each other. We'll come into that term later. Every entry is exactly the opposite sign from its corresponding entry. And when you add those two together, you always get the 0 vector, or 0 matrix. These two happen to be vectors, so it'll be a 0 vector there too. Okay? And then let's look at D. Okay? Go add 2, 1, 0, 4, 0, negative 1. I can't write, goodness gracious. Add to that 0, 1, negative 1, 3. Okay, what do you get as a result? You can't, because those are different sizes. Now, the book doesn't do this, but I'm going to do it. What if this negative 1 was a 0? Can you add them now? If that was a 0. No, you still can't. Even though that last column doesn't contribute anything, it's still a 2 by 3 matrix. Trying to add to a 2 by 2 matrix, you can't do it. They've got to be the same size. No matter what the entry values are, zeros or whatever, that doesn't matter. They're two matrices of different sizes. Perfect. Okay? When you're working with matrices, and then you introduce a real number. Now, you could be multiplying by the real number. You could be dividing by the real number, as long as it's not 0. You could be doing something with that real number to the matrix. That's okay. You can operate with real numbers. And that's what we're going to deal with in the next couple of steps here. Some legitimate operations you can do with real numbers. Oh, and those real numbers are called scalars. When you're dealing with matrices or vectors, and then you're dealing with real numbers that are not matrices or vectors, you call those scalars. Back in arithmetic, when you weren't dealing with matrices, you just called them numbers. But here you're dealing with matrices and or vectors, like these two, those three there actually. When you're dealing with those, then a real number in front would just be called a scalar. Okay, so that leads to the definition of scalar multiplication. And let me clear my slide here. To multiply a matrix A by a real number C, goodness gracious, my eyes hurt, or scalar C, you multiply each entry, every entry in that matrix, by that same scalar C. Okay? So to write it a little more formally, if A is a m by n, let me not put equal sign, that makes it look too much like an equation. Let's just keep it verbiage now. Is an m by n matrix, okay? And C is a, can't talk now. And C is a scalar. Goodness, I'm going to make it through 4.5 hours of class this afternoon. I don't know. My morning class went pretty well. I think part of the problem is I'm writing here and reading from the book, whereas this morning and this afternoon, I'll be able to read from the screen. That doesn't hurt my eyes like reading from the book, because I can't get the book to focus well. I have to get too far away, and then the letters are too small to see. Okay, if A is an m by n matrix, C is a scalar, then the scalar multiple of A by C is also an M by M matrix okay, given by CA is equal to C times AIJ. So what maybe you are anticipating, that's what it is. Now, that's every entry. Every entry, every AIJ in that matrix A is multiplied by the number C. Not just any old row or any old column, every sinking entry is multiplied by that C. You sort of distribute it across there to every one. Now, with that in mind, what if your C was a -1? Okay? If C was a -1, then minus A represents the scalar product represents the scalar product. My writing's getting really bad. I can't see what I'm writing. -1A. Okay? They actually put the parentheses around the -1. I'm not sure why, but -1A. You multiply -1 by every entry in that. Now, if A and B are the same size, I'm going to go to a clean page. Is that okay? Okay? Oh, okay. No. I didn't know if you're copying this or what. Goodness gracious. Sorry. Gotta remember to bring those glasses every day. Okay. Now, if A and B same size, and we'll call it M by N, just to be consistent with what we did before, then you can also do this, A minus B. Well, how is that defined? That would be the same as A plus the opposite of B, okay, which we just saw. The opposite of B is A plus -1 times B. You just take the matrix B, negate every term in it, every entry in it, and then add that to matrix A. That's how you, quote, subtract two matrices. You change signs of every entry in the second one and add them, which is exactly how you subtract sign numbers. Change the sign of the second number and then add it to the first. Okay. So let's do example 3. Man. Here's matrix A. 1, 2, 4, I believe that says. -3, 0, -1. 2, 1, 2. All right. All right. Having trouble seeing again. B is equal to 2, 0, 0, 1, negative 4, 3. Boy, it helps to step back. Negative 1, 3, 2, I think it is. Okay. Here are your two matrices. Number one, are they the same size? Yeah, 3 by 3s. Then it says for these two matrices, find A is 3A. What would that be? 3, 6, 12. I'm sorry. Oh, yeah, that's the 4. Yeah, I'm sorry. This is a 4. Yeah, that's a 0. Okay. I can't hear. Negative 9, 0, negative 3. Next. 6, 3, 6. There is 3A. All right. The B part asks, negative B. What would that be? Negative 2, 0. No, that's a 0 there too. Oh, you said 0, 0. I only heard one.
Yeah.
Or are you going down?
Yeah, I was on the second one.
Okay, yeah, that's fine too. Okay, going down. Negative 2, negative 1.
Well, no, I was saying, like I had said negative 2, and I said 0, 0.
Oh, I didn't hear the second 0. Okay.
I was moving on to the second one.
Okay. All right. What do you get next? 4, negative 3, 1, negative 3, negative 2. Perfect. There's negative B. Now, the C part here says what is 3A minus B? One, 6, 12, negative 10, 4, negative 6, 7, 0, 4. All right, let's see how they did. 1, 6, 12, negative 10, 4, negative 6, 7, 0, 4. Perfect. Any questions on that? Now, that was really nice of them to do the first two steps of the third one for you, so all you have to do is combine. So that was decent of them to do. All right, so we've added and subtracted matrices. We've multiplied by a constant, a scalar multiplication. Can we multiply two matrices? Yes, you can. But there are a couple of different ways to do this, okay? And, well, no, I'm sorry. I was thinking vectors. But matrices, yeah, is just the one way. Now, here's what they're doing. And they start with this example that hopefully you can relate to. And we're dealing with matrix multiplication. They're going to show you the example that you probably can figure out on your own, and then generalize that into a rule, okay? what they have is a football stadium. Must be from the South, huh? Okay. Football stadium has 3 concession areas. Okay. You have the South stand, the North stand, and the West stand. They must have taken out whatever is on the East stand. Maybe that's the big entrance or whatever. Okay. Now, each of these are located let me see if I can figure out. Goodness, I can't read this. There's 3 concession areas located north, south, and west stands. Okay. Now, the top selling items are peanuts, hot dogs, and soda. They're not from the South. We'd say Coke. No, I'm just kidding. But we'd say, no, I guess soda would be okay. Up north they say pop, and that's just not used too much down here. Soda, I guess, would be all right. That we all say Coke, okay? Even if it's not Coke, okay? Even if it's not a cola, you know, we still say Coke. Give me a Coke, okay? Sales for, okay, the top selling items are peanuts, hot dogs, and soda. So that's going to be represented by the columns here. The rows are going to be your stands, and you have peanuts, hot dogs, and sodas. Okay? Now, we also have the selling price. Yuck. For each of these. And this would be your peanut selling price, your hot dog selling price, and your soda selling price. Okay? Now that's just a vector. It's just that selling price is a big that word. Okay? And this is $2. What a rip. This is $3, and this is $2.75. Give me peanuts any day before the other two. It's the cheapest, but I still like them best. Okay? Now, they give you the sales, number of items sold. Peanuts in the South stand was 120. Bags, I'm sure. Hot dogs were 250, and sodas were 305. The North stands 207, 140, and 419 if I can read. Okay. The West stands must be much smaller. That's 29, 120, and 190. Okay. Now, if you were trying to determine what your total revenue was, because the selling price is the column vector there, and your number of items sold was your matrix over here. If you're trying to determine that, and stiff when I sit too long. I want to point something out to you. What your columns are here correspond to the rows over here. And it has to be that way. Okay? This is number of items. This is selling price per item. So your product of these is going to be an amount of revenue, okay? What you would do, 120 peanuts times $2 a bag, plus 250 hot dogs selling for $3 a dog, plus your 305 sodas for $2.75 each. That would give you your total revenue from the south stands. And then the north stands, you would do similar. 207 times $2, 140. Add to that 140 times $3, and add to that 419 times 275. Okay? Now, they didn't mean this to be all that realistic, but if you think about it, the north stands are going to have the southern sun on them. The south stands are going to be in the shade part of the time. They're drinking a lot more soda here than they are up there, aren't they? West stands are just smaller stands, obviously. There's not as many people there. That's beside the point. And the west stands would be 29 bags of peanuts for $2 each, 20 hot dogs for $3 each, plus 190 sodas at $2.75 each, and that would give you the total revenue from the west stands. So what you wind up with stands are here, and your product here. I don't have room to write it in like they did in the book, where they multiply each of those out. I wish I did have room, but I just don't. But what it's going to be is total revenue, which is dollars, right? And this is in dollars, okay? And this will be by stands. North stands, south stands, south stands, north stands, west stands, okay? Now, if you'll notice this, your peanuts, the interior thing, peanuts, they don't show up anymore. It's just stands and revenue. The stands were in the first rows before. They're still in the first row. Of course, there's only one entry there. This one was dollars, and that's what's in here too, okay? So your items, the peanuts, hot dog, sodas, they kind of lose their meaning because they're all melded in with this. And sure enough, these rows stay the same, and this column stays the same relative values, okay, representing the same thing. The stuff that you would think is almost the important stuff is panned out, and you don't have any distinction of that in the last, okay? Now, I don't know if that made any sense, but here is the definition for matrix multiplication. I'm going to see if I can get this down here. If you have some matrix A, okay, and M by N matrix, okay, and B, that's Bij. Now, just a little point here. Our example there was a 3 by 1 for B. B doesn't have to be a column vector. It can be a matrix just as much as A can, okay? And that shouldn't be Ij. I don't think, but I can't read. Yeah, they're calling Ij. I'd rather not, but we will. But here's the important thing. It's an N by, what do they call it, P? N by P matrix. Okay, time out, and let me point something else out. we just multiplied two matrices here. One was a 3 by 3, the other was a 3 by 1. Hey, they're not the same size. Not at all the same size, okay? And yet we can multiply them, and it makes sense. You can't do that with adding, you can't do it with subtraction, and you sure can't do it with equality. But here with multiplying, they do have to be. But here's something else. The number of columns of the first matrix has to be the same as the number of rows of the second matrix. That's not a happenstance, it has to be. It's not an accident. It has to be that way. Okay? That's why I wanted to call this JK here. But the I's are only going from 1 to N and the J's from 1 to P. This I is going from 1 to M and this J is going from 1 to N. So I would have preferred to change the subscript too, but it doesn't matter. Those are just kind of dummies there anyway. Okay. So if you have that, then the product AB is going to be, okay, now remember I said the columns here, number of columns here, has the equal number of rows there, and if they are, wipe them out, and your result is going to be an M by P. So just like the peanuts, hot dogs, and sodas, where your columns in one, the rows in the other, and then they didn't show up anywhere individually in your answer. Okay? So your AB, the product matrix, is going to be an M by P matrix. Okay? And that AB, the product matrix, is going to be some entity Cij. Okay? This time your I is going from 1 to M, and your J's are going from 1 to P. Okay? Where, now this is the part, I never sit down and memorize this, but Cij is equal to the sum can't get this far enough away. I think that's a K down there. K equal 1 to N. Yeah. K equal 1 to N. Okay? Remember, N's the thing we lost up here when we multiply them. Of A, I, K, B, K, J. Nope, that's not how they do it. Yeah, it is. AIK times B, K, J. And then they write it out for you. That's the part I'm having trouble seeing. AI1 B1J plus AI2 B2J plus AI3 B3J plus ... all the way up to plus AIN BNJ. Okay. That's what your summation turns into. Now, is that helping me remember or see it? No, that's just, it's true, but it's just a really awkward way of doing. That definition means to find the entry in the ith row and the jth column of your product, multiply the entries in the ith row of A to the jth column of B and then add the result, term by term by term. And that's why the ends have to be the same. So you have the same number of columns here, you're adding to the same number of rows here, the products, because you can't have any left over here or here, they have to be the same. So that's why the ends have to be the same number. Okay? So that's their way of describing it. I'm going to show you how I like to do it. If you like a better way, a way you understand better, go for it. You know, you paid your money, you take your choice. Okay? Here's matrix A, -1, 3, 4, -2, 5, 0, sorry, matrix B, -3, 2, -4, 1. Okay? Can you do AB? Can you do the product A times B? Yeah. Okay. Why? A's A. Yeah. Okay. Yeah. A is a 3 by 2. B is a 2 by 2. So the product of AB is going to be, these two have to be the same. They are, wipe them out. So AB is going to be a 3 by 2. Now here's what I do. You don't have to do it this way, but this is how I do it. Okay? It's going to be a 3 by 2, so it's going to be 1, 2, 1, 2, 1, 2. Right? It's going to have those 6. 3 rows, 2 columns. Okay? Now, key here is this entry here is going to be the 1, 1, 2. So what you do is take the first row of A, multiply it by the first column of B. That would be 3 is minus 9, right? Okay. So that's the -9, okay? What's the entry number here? 1, 2, right? So take the first row of A, second column of B. -2 is 1. Perfect. Okay? What's the entry here? 2, 1. So take the second row of A, first column of B. -12. Plus 8. -12 plus 8 is -4. So that entry is a -4. My writing is not too good. Goodness, it's getting worse. Okay, let me make that a -9. Okay, what's the entry number here? 2, 2. So take the second column of A, second row of A, second column of B. 8 minus 2 is 6. Okay? So that entry will be 6. All right? What's the entry down here? 3, 1. So take the third row here, first column there. Okay, which is -15. Okay, and what's that last entry here? The 3, 2 entries. So take the third row of A, second column of B, and that would be See if I, 10. All right, let's see how we did. Negative 9, 1, negative 4, 6, negative 15, 10. Yes. Okay. So, now they're saying what I said earlier. Put your sizes here. If the inner two numbers are the same, wipe them out. The outer two numbers gives you the size of your answer. And that's where I like to go and write down, put blanks there, exactly the right number of sizes, and then by the address of each one of those, row, column, that determines row of A, column of B, how you multiply. Now they do have a little blurb here on this page 43 about Arthur Cayley, a British mathematician, and he gave an abstract definition of a matrix. He was a Cambridge graduate, lawyer by profession. We won't hold that against him. Began his groundbreaking work on matrices as he studied the theory of transformations, blah, blah, blah. But notice here, Cayley and two American mathematicians, Benjamin Peirce and his son Charles Peirce, are credited with developing matrix algebra. Okay, so you see there at least 3 different paper topics there in the people, and then maybe matrix algebra, let's see, theory of transformations. You can find, he also was instrumental in the development of determinants, which will be chapter 3, will be in next. So anyway, lots of potential paper topics just from that one little blurb. Now that blurb can't be your source. It can be your source of your idea, but you have to get your sources somewhere else. Okay. So I think we've already established our general pattern for matrix multiplication. Have any questions about it? We'll, I think what I was doing is the same thing to do at the top of page 44. Let's do the little discovery here and see what we get from that. Sometimes these are instructive and sometimes they seem like they just take up time. Okay, so let's do this. They're pretty easy. These are both small 2x2s. 1, 2, 3, 4, pretty creative matrix there. And B is 0, 1, 1, 2. Are we running out of time? We got what? 2 minutes? Okay, yeah, you're right. Yeah, so let's try to get this done quickly. No, it won't be quick. Let's start there next time because it has 2 things for us to do, adding and multiplying, and do them both 2 different ways. So we'll start with the discovery next time, which means let's go to the back and see what homework exercises. You can do either 1 or 3 or both. They're pretty easy. Any of the odds 5 through 11, and they're pretty easy too. Do either 13 or 15 or both. And by the way, all these are in the answers are in the back of the book, but also you can go to calcchat.com for worked out solutions for these odd number exercises. That's why I give you the odd number. Okay. Then finding the product. Okay. I know you can do 17. Think you can do 19. I'll say do any of those you want to, 17 to 29. We're going to be doing more of those later, so if you don't want to do them all, you can wait and pick them up, excuse me, when we get to them. All right. That use most of the rest of our time? Okay. All right. We'll end it there then. I may be cheating you out of